So I did post an announcement sort of laying out the remainder of the review sessions. There was a little change. GSIs will be putting on a review session with 1 to 3 on Wednesday. I had planned to do something at 2 to 3, an office hour, but it's pointless to have a conflict between us. So I switched my office hour to tomorrow at 4 o'clock. Turns out I have something to do in the afternoon, so I can't get away earlier. So if you want to come at 4 o'clock to my office, you're welcome to do that. It's in that notice. So we'll have tomorrow my office hour. Wednesday will be GSIs from 1 to 3. Thursday, nothing. Friday, there'll be a lot because I wanted to give you my office hour, which is 2 to 3. Then I'll come here from 3 to 4. And then the GSI is going to go from, I think, 4 to 6 or something. So you can do that. So that'll keep you able to do this week if you want to do it. If that's all you have to do is physics, that's great. I'm sure that's not all you have to do. The university sees to that. Keep you really busy. So I hope there's no question on that. Are there any questions you want to raise on style? Of course, the exam is a week from tomorrow at 7 to 10 in Wheeler Hall. You've got a notice to that effect. So my usual procedure in something like this is to elicit your questions, try to organize in some kind of a logical way so we can proceed from one idea to another, and go from there. So if you have specific questions, let's hear. Yes, Renee? Okay. You're speaking of radioactive decay. Right. Okay, that's a good topic. Okay. Yes, ma'am. The what? Oh, okay, potential wells. Yes, yes. Yeah, that can be pretty obscure, although it's once you get it, it's good. Yes. Semi-infinite. Okay. In other words, finite, we would say. Okay. I don't know what semi-infinite would be. I mean, infinite is pretty far. Half the way infinity is infinity, isn't it? Yeah. Okay, yeah, I see what you mean. Okay, so like 1 and then maybe something like that or something like that. Oh, yes, that's a good one. Well, potential wells come up quite a bit actually in our subject because way early we did cover. We started out with electric fields. But before you knew it, we were starting to talk about potentials, and it's the same potential that we're talking about here. So this comes up, even with classical things. So yeah, it would be nice if we really went over that nice and slowly, which we didn't probably do adequately in the run-through up to here. Yes, sir. What? Quantization. Sure. That would be somewhere in here, I think. Like where it comes from and what? Yes. How it's related to the periodic table. Yeah. Okay. Yeah, I'd like you to know that, if nothing else, just to be in awe of how far the human brain has gotten to see all this myriad of things in the world and how we can understand it on a relatively straightforward basis, on the basis of quantum theory. That's quite a handful right there. Anything else? If you think of something, if I don't say it clearly the first time, we can go over it some more. Yeah, so good, let's go. Well, see, if I were thinking about this, what I would think of is the first thing we learn is that electric charges exert forces on each other. That's a very primitive idea that we started out in lesson 1. We had the idea that you could pick up some static charge, and even if you bring it to a neutral object, you bring it near here, you can get this neutral object to be attracted to this charged up ball. So there are forces between these things. We could pick up little pieces of paper or make a fifth ball move around and so on, or be attracted. And the way we understand that is that the plus charges repel each other. In the case of, I think we had something on a rod on a point, something like that, and you can bring this near another neutral ball, but what it'll do, somehow it will distort the thing, and you'll get negative charges closer to positive charges, and so you'll actually get an attraction between these. I think I had something like a little experiment like this. Wasn't that nice? And all it is that this is a dielectric material, and it contains plus and minus charges. They're in balance normally, but if you bring a field of charge near it, it pushes the plus charges away, attracts the plus charges to it, and because these are closer, the two things attract each other. So this type of material we would call a dielectric, and the reaction of a dielectric to a nearby charge is to have a force acting on it. We describe that by saying, well, this object here, one way of looking at it, is that it's creating an electric field around itself, such that a plus charge put into that field will feel a force going away. So we say charges create a field. So that's really the basic primitive observation that we have. And okay, then we move to the idea that there is a potential energy. Well, first we have a potential, and then we have potential energy. So where does this come from? Well, it comes from the idea that if you are a plus charge in an electric field, and you are moved in that electric field, if you move against the field is trying to push you this way. If you move against that field, the field does work, exerts a force on you this way, and if you take the amount of force that let's see, you have to be careful here. The work is done on the field, so it's the opposite of the work done on this charge. So you have, let's see how to best express it. the work done by the field is, let's see, we have to, okay, so if you have E dot dr is, this is the work done by the field, QE dot dr is the work done by the field. The change in the potential energy is equal to the negative of this work done by the field, E dot dr. This we define as the change in the potential energy. And we have the idea that you have the change in the potential, which is the change in the energy per unit charge, right? So that's equal to minus E dot dr. So we have the ideas that, the important idea that the change in, very simply, the change in, oh, by the way, this is an energy. See, this is work. This is a force times a distance. This is a force times a distance. So, oh, I did say it was work, which is an energy. Okay. So the important idea that you want to have is that the change in the potential or potential energy is, in a way, the rate of change of that is equal to the field. So, for example, if you have something like a capacitor, which has plus and minus charges on it, the electric field is going in this direction. The electric field is the negative of the change in voltage or potential with respect to distance. So, for example, if we start with the, let's say V equals 0 here, you will have that the V is equal to a lower amount by E dot the separation here. So the interesting thing is that what you can do is if you have a potential difference between 2 points, roughly speaking, you can get the electric field by simply taking the change in the potential with respect to that change in distance, or L. So, for example, the electric field in here would be the voltage that I put on this plate over the separation of the plates. It's volts per meter in units. And volts being an energy per unit charge, yeah, you want to remember that volts is the energy per charge. Okay. Okay. Actually, there's a negative sign. So actually, the electric field is going in this direction, and you have your what's called equipotential lines running perpendicular to that. So a plus charge, you see, would go in the direction of the field. The field is doing work on the charge, because the field, the force, and the distance are going in the same direction. The potential difference is actually, that work becomes positive. So E times dr, that work is positive, moving from this point to this point, but the change in potential energy is negative of that. So the change in potential energy would be negative, which is sensible, because what it says is that the positive charge has less potential energy when it's down here. By the time it arrives here, it has no potential energy. It has potential energy when it's up here. So in this case, what's happening is if you take that as the 0, the potential energy will go down as you go from this level to this level. Because here it has potential energy, because if I let it go, it can move. But by the time it gets here, there's no tendency for it to move any further. Well, that may or not be very clear, but the point is that where this comes up, for example, is, if you will, the photoelectric effect, as an example. Let me put it over here. You recall with the photoelectric effect, you have light coming in, and it causes electrons to be emitted from a target. And what we do is we put a repulsive potential or on a plate over here. Now, the electrons, when they come out, have a certain initial velocity, right? The reason being, according to Einstein, the photoelectric effect, the photon coming in has a certain energy given by the proportional to its frequency. The electron is being held within the metal, or whatever, material, by a certain potential energy. Well, that's a property of the material. It's a property by which, in the quantum idea, you have electrons in various states, and the question is, how much energy does it take to remove this electron from some state to make it a free carrier? In other words, ionize that carrier. That's basically what we're talking about here. When we talk about the work function, it's basically an ionization energy. The energy coming in, a certain amount of energy is needed to get you out of this highest filled electronic state. You need a certain amount of energy to get you out of that state and make the electron a free electron coming out like that. And you've absorbed the one photon. Okay. This is getting on and on. But here, the point is that, let's look at it this way. You have a certain energy of that electron when it comes out of the metal. That energy is kinetic energy, and it's given by the energy you put in, HF, minus the energy it took to ionize it out of the metal. So it has a certain residual energy which shows up as kinetic energy coming out. So if we draw a line here, half mv squared, this is what we start with. And then we're going to use the idea of conservation of energy, that we're starting out at this side with a certain amount of energy, a half mv squared, plus potential energy, and that's going to be our total. And when the electron arrives at moves across, there is a potential well here. The potential energy, because this is a negative charge coming out, the potential energy, if you have a certain voltage here, well, yeah, E times that voltage is the potential energy when you arrive at this point. So depending on how much voltage in this demonstration that we had, we saw that you could put a negative potential here. The potential energy we give E times E. So the potential energy will equal E V. If you arrive here, you arrived at the total voltage that you put on. There's kind of a, oh wait, I got that right. It should be more like, I want it negative. I want it negative here. I want a negative voltage. So I'm trying to establish the stopping voltage. The stopping voltage. So if I put on a certain voltage on this plate, an electron starting out here is actually being repelled by this plate as the electron comes across with its speed. And it will go, its total energy is given by its kinetic energy plus its potential energy. And here's its potential energy as it goes across. It reaches this amount here is E times V, the V applied here, which is actually in a way variable. It's like an adjustable battery. So I can rise up to a total potential energy like this. Now the question of whether the electron arrives is whether its kinetic energy is higher than the potential energy that it's accumulating. Because the electron, as it goes across, the field is actually in this direction, minus the, let's see, no. The field is this way. So that would be the direction of the force on a positive charge. The force on a negative charge is, of course, this way. So this electron, as it's coming across, feels a force pushing it the other way. So it actually increases its potential energy. So the diagram you can draw is this is the potential energy that it's accumulating as it moves across. But so the actual kinetic energy, this is the total energy here. It starts out at a half mv squared at this point. That's the total. Now this is the potential energy. This amount here is the kinetic energy. You see, and this amount here is the potential energy. This is maybe overkill, guys, but I'm trying to show you how these potential diagrams work. You start with a total amount of energy, which is supposedly constant. But it's being converted from kinetic, which starts out as kinetic with no potential energy. And as it goes across, it slows down because it's in a field that's exerting a force the other way. So it's slowing down. It's accumulating potential energy, which is this much. And this is the residual kinetic energy, like this. And if there's enough kinetic energy, it will still be moving when it hits the plate. So it will actually reach the plate. On the other hand, if you raise the potential energy by raising the voltage that you apply, let's say you put on a voltage this much from the battery. In other words, I increase the voltage on the battery like that. Then what happens is you start out with a certain total energy. At the beginning, it's all kinetic. The particle goes across, and its potential energy is increasing. That's the yellow line. It's increasing. The kinetic energy decreases until the kinetic energy is equal to the potential energy, at which point the particle stops, right, and rolls back down, is forced back down. So in that case, a particle that started out with this kinetic energy would run up here, and you've seen that in that demo. It sort of stops, and then it goes back. So this is the furthest it can go, and it gets that way by rolling up its potential barrier until it stops here. Now, the stopping voltage is the one at which the particle just barely reaches the plate. Namely, if you get the voltage to be just here, it's the stopping voltage. This one would be the stop. Because there, it's the electron, the fastest electron just barely gets there, at which point the current stops. Beyond this blocking voltage or stopping voltage, the current stops. Because this flowing electron is a current. So if you plot the current versus the voltage applied, this one here, the current will go down until you reach the stopping voltage. And at the stopping voltage, no electron can get across, so the current goes to 0. So this is the meaning of the potential well, or potential barrier, in general. And here's that's the application to the stopping of the photoelectrons. In the case of, okay, yes?
Sorry, I'm a little confused here. So we're talking about a battery.
Down here's a battery.
So are you saying that we can only have up to a certain limit of the voltage difference for a battery?
No, I'm not trying to say that. I'm trying to, the question is, does it limit the voltage of the battery? No, the battery I'm considering is just a way of applying a voltage, sort of like